All right, line P1, we're in learning test 7b. We're going to do all of our parallel transformer calculations. And we've already done transformer calculations, how to use our VA to go and establish our values of volts and current. But now what we're going to do is we're going to move on into doing a couple of parallel sets. In the previous learning task, we've covered over the conditions that have to be met anytime that we are going to go and parallel up transformers. The conditions are going to go and be that they have got the same amount of impedance, that percent impedance is going to be the same, and that they are going to go and have the same voltages available, in this case, 2400, 4800, and 12240. Excuse me. And then that last of all, that they are going to be connected to the same polarities. These ones over here are going to be done properly. Obviously, if we're going to be connecting a transformer that is going to be for 2400/4800, we would be connecting, if it's a 2400 volt bus like we have over here, we would have to go and choose a parallel connection for that. So if I take a look at that, I see that all of my odds for both of these transformers are going to be connected over to my line 1, and I see that all of my evens, both of these transformers, are going to be connected over to line 2. Sometimes they draw them like this, other times we've seen where they draw them in like that, and then they would just go and skip them like that. Either one of these works because it's ultimately going to be connection to the correct line. So we've got our high side, which is our primary in this case, that has been connected properly. We're also going to go and take a look at our low side. Now our low side, what we're looking for over here is a 120 volt bus. Once again, what's my rating on here? It's a 120/240, which means that if I'm going to be connecting this thing for the lower value, I have to be in parallel once again. So I'm going to see that all of my odds are going to be connected to the same lines over here, and that all of my evens are going to be connected to the same lines as well. So we verified our transformer connection that we have inside here. Just because it's what we're supposed to have doesn't mean that they've always drawn them correctly. That's why we go through these things to go and make sure. The next thing that they go and tell us is that we've got certain KVAs for these. I'm just going to erase all those because I don't need to have those anymore. We've got certain KVAs for each of these. This one here is going to be 167.5, which seems like an odd value, but it's actually a very common value. We'll take a look at that in a minute. And then this one over here is going to be a 37.5 kVA as well. You note that that's half of a 75er that we would have off of that. They want us to calculate everything that we're going to go and have. So they have drawn the schematic. They want to find out the total kVA of the bank, and they want to find the full load current ratings, etc., etc., etc. We're going to start with the total kVA because we prefer to work in power because power does not lie to us in the same way that some of our other values can. We can always add values of power. So for my maximum that I could go and have for kVA delivered would all be dependent upon load, but at the maximum, this one could do 167.5, this one could do 37. So I'm just going to go and add those two together. 167.5 plus 37.5, which is going to go get me out to a value of 205 kVA. kVA. So that's going to be my total capacity. 205 kVA. I'm going to place that up top because it spans over top of both of them. kVA in is equal to my kVA out that I'm going to go and have. So therefore, this side over here must also be 205 kVA over here. Next thing that we're going to do is we're going to find what is the total amount of current that we could go and deliver out of here. Well, if I'm delivering 205 kVA at 120 volts, I can go and take my VA and divide out my volts. It's going to leave me strictly at the amp. So I'll take 205 kVA divided out by 120, and that tells me that what I can place out of this bank is going to be 1708 amps that I will have out of it. Lovely. So 17.08 amps that we can deliver out of it. In order to deliver 1708 out, how many must we be putting in? Well, we must be putting in an equivalent amount of kVA once again. So I can go and take my VA and I can divide out my volts, which will tell me my total amount of amps that I'm going to be taking into this circuit over here. 205 divided by 2400 gets me to 85.4 amps. So I'm just going to draw that up top here, 85.4 amps. I'm just going to draw that actually with an arrow going into here, and I'm going to draw this with an arrow coming out on this side over here, 1708 amps coming back out of that bank. Later on, we're going to apply Kirchhoff's current law, and we're going to go and verify everything that we're going to go and have. The next thing that they ask is what's the full load current ratings of each of my transformers that I'm going to go and have here? Well, how many kVA is this one delivering? 167.5. At how many volts? 2400 volts. So I can go and take that 167.5 VA and then divide out my voltage of 2400. So I'm going to use that same VA over V, but now I'm just going to do this VA. We're working inside of this individual transformer here. So we'll take 167.5, divide it by 2400, and when we do so, we find out that what we're feeding into this thing is going to go and be 69.8 amps. So I'm just going to put that up here, 69.8 amps primary. Later on in a little bit, we're going to actually split up that 69.8 amps that we have listed over there into the individual sections of our multi-coil transformer. But for now, we'll leave it at that. Let's do the secondary side as well. Once again, total VA, 167.5. We're going to go and divide it by the voltage that we're putting it out. We've got them in a parallel connection, so 120 volts, which tells me that this bank total on its secondary over here is going to put out 1,395.8 amps secondary. We're going to do the same now for this one over here. We're going to go and take its kVA, so 37,500. We're going to divide it by its primary voltage, 2400, and that's going to give us a value of 15.6 amps that I'm going to go and have for it. And then we're going to do the same thing for its secondary side over here, 37,500 divided by my secondary voltage. The connection's for 120, so 37,500 divided by $1.20 gets me to 312.5 amps. Lovely. Okay, so if I now take a look at my individual windings, each of my windings is going to have to be half of what my overall transformer itself is able to go and put out, right? This would make sense that we would have to have these things equally sized. So I'm going to go and take a look at my individual windings right now. We're going to develop what current we have inside of each of them. These ones are going to go and be smaller values. We're going to take this 167.5. The first thing we're going to do is we're going to go and split that in half. And when we split that in half, we find out that each of my two sides are going to be good for 83,750. It's half of 167.5. So 83,750 VA is what each of those sides is good for. So I'm going to take this VA and I'm going to divide out my voltage that's placed across it. I see it's 2400 volts placed across 83,750, which tells me that this one over here is going to have a grand total of 34.9 amps going through it. Therefore, this one must also 34.9 amps going through it. And then on my secondary side, so I'm just going to erase those arrows now. We don't need them anymore. It's going to be the same thing. I'm going to check my voltage. This coil is over top of 120 volts. So I'm going to take 83,750 divided by $1.20 gets me to 697.9. 697.9. And then this one over here is going to be good for the same thing, 697.9. We then go over to this one. Once again, we're going to take the total VA, because that's the VA of all the coils together, split that in half. When we do so, we are going to go and find out that our individual coils, very similar to this one, just going to be 18,750 now that we're going to have from this one and from this side of the transformer. Once again, we're going to take our VAs, we're going to divide by our values of volts that we are going to go and have. When we do that, we'll take those ones out over there. We'll start with this one over here, 18,750 divided by the voltage that that coil is placed across, 2400 over there, gets me to a value of 7.8 amps. This one would also have to be 7.8 amps as well. They're equally sized. We go to the bottom side over here, the secondary, 18,750 divided by 120 is going to go and get me to a value of 156.3 amps. This one over here would be 156.3 amps. Some of you are saying that seems like a lot of work, a long ways around there, Joel, to go and place them like this. It is, because if you take a look at it, these two can be added together to go and form 312. Try it. 156.3 plus 156.3, 156.3 plus 156.3 equals 312.6. There's a little bit of rounding error inside of there, but it's nothing, critical. We get that it's the same number that we have. This one is going to be the same thing. You take the 679 and the 679, or 697.9, sorry, I struggle with this number for some reason. 697.9 plus the 697.9, you end up with this 1395.8 that we're going to go and get out of it. Even better yet, if you would take each of your currents and you were to add them all together, you are going to come out to 1708. We're just going to try that. 1395 plus 312.5. 1395.8 plus 312.5 gets me to a value of 1708. We satisfy Kirchhoff's law. It's Kirchhoff's law of current and Kirchhoff's law of voltage. The total amount of current that's coming in is going to be the same amount of current that's going to be coming back out. The total amount of VA in is also going to be the total amount of VA out that we are going to have down over here. It's a wonderful, wonderful thing to be able to see these currents, add up. And if you want it, you could place an instantaneous polarity. If I did, we'll just go with a blue. We'll say that maybe this line over here is going to be my positive, which would mean that this would have to be positive, this would have to be positive, 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 like that. If H1 is positive, that would mean that X1 would have to be positive as well. That looks like an X, which would mean that that would be our positive over there as well. If you were to go and follow the currents, you would be able to go and see that the 1708, if we've got a load connected, we could draw up to 1708. Now, we don't necessarily draw 1708. If we've got nothing connected like that, no current's going to go and flow in the secondary. Therefore, no current is going to go and flow in the primary. To be honest, there will always be a couple of amps, just the magnetizing current inside of the primary. But outside of that, we should not see anything on our second or on our primary side. It's only when we go and apply load and increase the amount of load that we're delivering out that we'll be able to get all the way up to this 1708 amps that we'd have out of it. If you'd want, you'd be able to go and take all of your current values and you could just draw them, add them all up together. 156.3 plus another 156.3 would mean that we then got 312. We're going to add that one in there. So now we'd be at 312, 312 plus 979, or 697. We'd add that onto there. I don't know what that one's going to get us up to. And then we add this one onto here. And what we would see is that every single time Kirchhoff's law of current would be satisfied all the way through, we'd end up with 1708 coming out. And then going back in, we would go and have 1708 entering. And then we would take 697 off. And then we would go up to here and we would take another 697 off. And then we would go through up to here. And we take off 156. And then that would leave us with just 156 over here. That would leave up that line, and then we see that we form those complete loops. You can track through off of Kirchhoff's current law with these. Okay, individual winding currents aren't going to be super critical to most of our installations because usually what we're looking at is we are looking at the overall that we are going to go and have. This 1395, this 312.5, this 15.6, this 69.8. Because those are going to go and determine the size of the fuses and circuit breakers that we're going to go and use to protect our transformers on the input as well as on the output side. We could go and place protection on either side. It's not going to be required to be on necessarily the primary, but it's very common that we're going to place on the primary because we do know that the code has the requirement for a disconnect in the primary. They don't show it inside here, but in most cases, I'm going to go and have that disconnect in the primary, which means that if I'm putting a disconnect, make it a fusible disconnect. Stick the fuses inside of it, and it just eliminates one more piece of gear that you would need to have on the low side. Let's take a look at these currents that we have over here, and let's find out what this transformer setup would do underneath a fault. The first thing that we're going to go and do is we're going to go and take a look at our secondary side. Our secondary side over here has got 1395 amps plus 312.5 amps, and altogether it's getting us out to 1708 amps that we are going to have out. We're going to start with the 1708 amps because that's what we're delivering out of here. If I've got 1708 amps at a 3% impedance, I guess I could have left that, 1708 divided by 0.03, that means that I've got a total available short circuit current, if I were to short this bus together, of 56,933. It's a little different than your book, but that's rounding errors inside of there. 56,933. 56.9 kilo amps short circuit. That's going to be my total available amount. Part of that is going to be delivered by this. If you take 1395.8 divided by the 0.03, you're going to come out to 46,527 amps short circuit. And this one over here, if you take that 312 divided by the 0.03, you're going to end up at 10,417 amps short circuit. If I get a lot of amps going through on my secondary, do I also get a lot of amps going through on the primary? Well, absolutely. If I get 59 or 56.9 kilo amps traveling through the secondary, it has to come from somewhere. It's not magic, it's science. We're going to go and take a look at these amps coming through from this side. So we can just go and take that 85.4 amps up top there, divided by 0.03, which tells us that on our input side, we are going to go and have a fault current of up to 2.8 kilo amps that we would be delivering. 2.8 kilo amps. And this is going to be the short circuit current, not a short circuit over here, because obviously if this short circuited over here, then all of my amps, upstream would just go and circle around like that. They wouldn't go through the transformers. But this is going to be the amount of current that I would have if this side over here, the secondary, were to be short-circuited together. If I drop a bar across those two buses over there, then I'm going to go and deliver 56.9 kiloamps, which is going to cause 2.8 kiloamps to go and flow in my primary. Once again, make sure that your interrupting ratings are going to be able to go and clear this. We would need to have something that's going to have at least a 50 kiloamp interrupting rating for this one, and this one would need to have at least 10,417, so probably a 15 kiloamp interrupting rating on that one. All right, let's move on to our last one inside of this section over here. We're working with the same transformers, that same 167.5 kVA, but now we're going to go to our high voltage type of connection that we are going to go and have, where I'm seriesing these together. First thing I'm going to do is I'm going to go and verify that if this is correct. I've got 2400, we're using the same ones, 4800 volt rated transformers and 120/240 volt rated on the secondary or on the low voltage side over here. If I'm going to connect it from a high voltage on either then, the 240, the higher voltage, the 4800 is the higher voltage, then what I'm going to need to do is do a series type of connection. That's why we have these things crisscross. So we can either take them up to the same lines or we can series them together like this. What we take a look at is we have got all of our H1s connected to the same lines over here. And then we series through H2 ties to H3. And then we go to our line 2 with our H4s. We'll verify that on the bottom side as well. We see that X1 ties down to this line, which means that X1 of the other transformers should tie to the same line. We see we series through both of these, so they're set up for that 240 volts. And we see that we are dropping down to this line over here. Lovely. So we know our connection is good to go. Next thing we're going to do is we're going to go and figure out our total kVA ratings. kVA is, once again, a power rating, which means we add it up. We do the exact same thing as what we did in the previous one. In the previous one, we had a total bank that was good for 205 kVA. We are also good for 205 kVA here because we just take this kVA, we add it to this kVA. It's power. We just get to add that, right? We did them over here. We got 205 kVA. Now we've got the same connection. We're going to go and get 205 kVA once again. If I've got 205 kVA, but it's at my 4800 volts, we know that VA divided by my volts is going to go and give me my amps. So I'm going to go and take my 205 kVA and I'm going to divide it out by 4800. When I do that, it's going to go and give me an input line current that is going to go and be 42.7 amps. Over here, and it's going to go and give me on the outputs 205 kVA divided by my 240 volts. It's going to give me an output of 854.2 amps that I'm going to go and have back out of this. All right, let's erase all of that stuff so we've got some room to write a few other things. So this is going to be my input, this is going to be my output. Note that both the low voltage bus and the high voltage bus have doubled from the previous problem. And if I compare them to the previous problem, their values are now halved because the voltage doubled, right? When we did the low voltage connection, we were at 85.4 amps as its nominal current. Now that we're at the high voltage, we're at half of that, 42.7. And I take a look at my high voltage on the 240 bus over here, 854.2 amps. Compare that to 1708. It's going to go and be, because we're at a higher voltage, we get half the current, but the VA is still going to be the same. Let's figure out our VAs for each individual transformer. Well, we're going to go and take our value of VA that we put out for each one of them. So for this one over here, we're going to start by taking 167.5. We're going to divide it by 4800 because that's the value of voltage that the whole thing is placed across. It's a series connection, so we need to use the high value. 167.5 divided by 4800 gets us to a primary current of 34.9 amps primary. And if I take a look at my secondary, it's 167.5 divided by 240 gets me to 697.9 amps secondary. We'll do the same off of the smaller transformer over here. 37,500 divided by 4,800 tells me the maximum I could pull out of this one would be 7.8 amps on the primary side. And if I take that 37,500 divided by 240, which it's placed across over here, that's going to go and give me a value of 156.3 amps. If you take all my secondary current, 156.3 plus 697.9, and you add them together, you will come out to this value, or very close to, give or take a tiny little bit around it. Same with on my primary side. Kirchhoff's current law has to be satisfied. I bring in 42.7 amps, I dunk off 34.9 here, which means that I'm left with 7.8 that are going to be over here. It's just going to go and mathematically add together. Next thing that they ask is for us to develop the amount of current going through each side of this. They do it the complicated method. They take the kVA, they divide the kVA in half, and then once they divide the kVA in half, they put half of the volts. They divide their voltage in half as well. So they take 83,750 divided by 2,400. In all honesty, that's a lot of over-analysis if you ask me, because when I take a look at it, if I've got 34.9 amps that is flowing through this winding, guess what? All of it has to go through this winding over here. There's no addition. There's no nodes inside here where currents are going to be combining. Therefore, each of my individual windings, in this case, is going to be carrying the same as my line amps, 34.9. 34.9. You can do it their method. You can just take a look at it and say it's a series connection. It's got to be the same throughout as well. Or you can just take it, divide your VA in half, and divide your volts in half across there. 697.9. This one over here, same way. If I take a look at 7.8 amps, I see that all of it has to pass through this winding, all of it has to pass through this winding. So each of my individual windings are going to be good for 7.8 amps over here. Same with this 156.3. All of that 156.3 has to go through there, and then all through there. 156.3 through there as well. Lovely. Okay, so that gets us all of our full voltage values, or what we can load this thing all the way up to. Last thing that we're going to do is we're going to go and take a look at our total available fault current. Once again, let's start by taking a look at the absolute maximum that we could go and have, which would be 854.2, and it's the same 3% impedance. So we'll take gets me out to a value of 28,473. 28.5 kiloamps roughly underneath a short circuit. Nobody's metering it into a short circuit, but we do have to know what these values are going to go and be so that we're once again able to go and pick fuses and circuit breakers that can interrupt that value. If I take a look at each of my individual ones, each individual transformer is also going to go and have a certain amount of short circuit current. They each do their share to make up this amount over here. This one over here, if I take this 697.9 amps that I can deliver out of this one, divide it by 0.03, it is going to go and give me a grand total of 23,263 amps that I'm going to go and have as a short circuit current. That's going to come out of this one over here. This one over here, if I go and divide it by 0.03, it is going to go and give me out a grand total of 5,210 amps that I can have. And if I take this and I add it to this one over here, we come out to that value over there of 28.5 kiloamps, or roughly close to. There's a little bit of rounding inside there. Once again, the sole purpose of sorting these ones here is to make sure that we can engineer proper controls. Equipment, not just breakers actually, by the way, but even bus bar centers are going to go and have maximum fault current ratings. The reason for these is in a lot of cases going to be mechanical, because if I get 28.5 kilo amps, that's 28,000 amps, the size of the magnetic field around there is going to be absolutely astronomical. And if I've got a massive, massive magnetic field, that means it's going to go and repel from some stuff or attract towards other stuff. And underneath the fault current, there's huge physical damage that happens. Bus bars themselves will literally pick up and curl like that. Huge ones, stuff that's the size of your forearm or maybe your leg or whatever, will go, and underneath the fault current, they will get bent at weird and unnatural angles just due to the magnetic stresses that are going to be on it. So even though some equipment doesn't have breakers inside of it, splitters and bus bars, they're still going to be rated for a certain number of kiloamps, because that's the amount of kiloamps of magnetic stresses that they're going to be able to withstand. All right, that covers us off now for Learning Task 7. It's a long one. There's also a lot of questions inside of your self-test. Go and take a look at that one now.